A very good morning, children. I hope you had worked with the group 15 elements completely. I didn't explain in the last session about the oxoacids of phosphorus. Very short I expressed H3PO2 only expressed. But you need to work regarding the tablet data that is there in the textbook. I hope you had done it. And coming to the group 16 elements. See, these groups are having a very long concepts. You must read the whole textbook, children. And second thing is, I am making only synopsis of these topics. On the group 16 elements, what are the elements we find? Oxygen, sulfur, selenium, tellurium and polonium. Leveretium is a new element that is given in the syllabus, but its half-life is very short, so its chemical properties are not discussed. Now coming to these properties which are in common. First we had seen their electronic configuration. What is their electronic configuration? NH2, NP4. Any noble gas will be there here. For that followed by NH2, NP4 electronic configuration will be there. When we compare the yesterday's concept NH2, NP3 for what? Group 15 elements. In the group 15 elements, p orbital is half filled. Due to the half filled p orbitals, their ionization enthalpy is more. But here p orbital is having more than one than the half filled. So what they will say is ionization enthalpy of the group 16 is lesser than the group 15. Ionization enthalpy of group 16 is lesser than the group 15 because in group 15 stable half filled electronic configuration is there. In group 16 the stable electronic configuration is not there and these are having lesser ionization enthalpy. And coming for atomic radius. How about atomic radius in a group? As usually, atomic radius will be increasing. Atomic radius will be increasing top to bottom. Top to bottom. Everyone knows this one very well. And how about electronegativity? As the atomic radius increases, electronegativity decreases. Electronegativity decreases. So, which is a strongly highly electronegative element in this group? Oxygen is the highly electronegative in this group. And due to this highly electronegative element of this oxygen, so whenever it is forming some compounds like with hydrogen, the compound will be involved in hydrogen bonding. The compound will be involved in the hydrogen bonding. So due to the only case of electronegativity. Coming to the physical properties. What are the physical properties of these elements? Oxygen and sulfur are non-metals. Selenium and tellurium are metalloids. Polonium is an radioactive element. Here, oxygen, how does it exist? It exists as a diatomic molecule. Sulfur exists as an octatomic molecule. Means atomicity is more in case of sulfur. Hence, its boiling point or the melting point values, once you see there is an abrupt change. Means in case of sulfur, the melting point is more than the oxygen because the number of atoms given in a molecule are more. Hence, that is covered in the physical properties. And coming to the chemical properties. In the chemical properties, you will be first observing about their oxidation states. What will you be observing about their oxidation states? Everyone knows that oxygen in general shows a -2 oxidation state. Means another element must be lesser electronegative than oxygen. But in the case of OF2, here fluorine is highly electronegative than oxygen. Hence, this oxygen will show a +2 oxidation state. And the remaining oxidation states of these elements are +2, +4 and +6. +2, +4 and +6. Down the group generally, +6 stability decreases. How many electrons are there in this element children? NH2, NP4. Totally 6 electrons are there. But down the group, like our tellurium, you can see tellurium. This tellurium, what you can find is Due to the intervening d orbitals, the s electrons will not be involved in bonding. Hence, in case of tellurium, plus 4 is the stable oxidation state due to inert pair effect. Down the group, plus 6 stability decreases, plus 4 stability increases due to inert pair effect. And coming with our oxygen, due to its small size, and high electronegativity, its boiling point is more like in the case of H2O and H2S. Once you compare H2 and the H2S, among these two, which is having more boiling point means you must not forget H2O is having more boiling point than the H2S, because in the H2O molecule, these are involved in intermolecular hydrogen bonding, but the electronegativity of sulfur is lesser than the oxygen. When electronegativity decreases, they will not participate in the intermolecular hydrogen bonding. Obviously, boiling point decreases. I hope you understood the point. Clear. Now, their reactivity towards other elements like hydrogen, oxygen and halogen. How to study? See, from this area, much important questions are being asked. So, reactivity towards hydrogen. These elements are reacting with hydrogen to form the corresponding hydrides. Like H2O, H2S, H2Se and H2 tellurium. See children, yesterday we brought one point. What did we brought? Oxygen, sulfur, selenium, tellurium. Imagining oxygen, sulfur, selenium, tellurium. Imagine this is hydrogen. So, whenever the size of the central atom is small, like oxygen, it can hold the hydrogen very strongly. Whereas when the central atom size is increasing, the nuclear distance is increasing from the hydrogen. So the hydrogen can be readily lost. So what is the problem regarding this? Means very important questions are coming in this area. The compounds like tellurium hydride, they can readily lose the hydrogen. Whatever substance is readily losing the hydrogen, we say it is more acidic. Second thing, it is acting as a good reducing agent. So, some points are asked in the previous year's exams, which is not a reducing agent among the following. Reducing agent means what, children? It can make another species to gain the hydrogen. When this is losing, it can make. What is the order? Generally, what is the reducing agent order in these hydrides? Water, H2S, H2Se, He, H2E. This is down the group. What is increasing? Reducing tendency is increasing. Or we can also say their acidic nature is increasing. Or we can say thermal stability order they may ask. Thermal stability order means which is more stable. See, thermal stability order means H2O is more stable than H2S, which is more stable than H2Se, which is more stable than HETE. Means HE2E is less stable. Means it readily decomposes. When it readily decomposes only, it can lose the hydrogen, so acidic nature will be more. Or we can say reducing order will be more. So among this, which is acting as least reducing agent or which does not make another species to undergo reduction is water. Got the point, children? So which is not a reducing agent means here we can speak water is not a reducing agent as its hydrogen is strongly held by the highly electronegative element oxygen. This type of questions are major, many questions are there in that area. So see that area, thermal stability, acidic nature and the reducing nature. Second thing, we can see how what type of oxides are they forming. They are forming the type of oxides EO2 and EO3. Among this one, the important concept is SO2 and SeO2 and TeO2. See, this SO2 and SeO2 are acting as a very strong reducing agent, whereas TeO2 is acting as a strong oxidizing agent. TeO2 is acting as a strong oxidizing agent. So this is a what important area to be studied, because we will be learning this concept again in the case of sulfur dioxide chemical property. Sulfur dioxide chemical property. So after this oxides, what had we learned? Reactivity with reactivity with halogens. Reactivity with halogens. Generally these forms, the halogens are the type sulfur. If you take, it is forming sulfur hexafluoride. Sulfur hexafluoride. It is generally highly stable due to the arrangement of a special orientation of the atoms. If you see the SF4, sulfur hexafluoride, how is the arrangement of sulfur hexafluoride, children? Sulfur hexafluoride. Is this not the structure of the sulfur hexafluoride, children? Sulfur hexafluoride. Generally this appears as trigonal bipyramidal. But this is also learned as a seesaw shape in your first year. In this case, the hybridization of the central atom sulfur will be sp3d hybridization. If you see our halides like sulfur hexafluoride, or you can see the remaining examples are also there. Coming for dihalides. In these dihalides, the central atom will be showing sp3 hybridization. What hybridization? sp3 hybridization. Whereas the sulfur can form monohalides with chlorine or with bromine. But those monohalides will readily combine to form dimers. Two of them will form the dimers. So they readily undergo dimerization. There are many dimers of these compounds like sulfur chloride or sulfur bromide or selenium dichloride or selenium dibromide. Among these, the pointing out question will be for objective is these dibromides undergo disproportionate reaction. The dibromides undergo disproportionate reaction. For example, Se2Cl2 is there. This is undergoing a disproportionate reaction. How? One of the selenium is combining with all the 4 chlorines and 3 seleniums are placed aside. So which one of these will undergo disproportionation means the dimer that is formed from the monomer will undergo the disproportionate reaction. Good. What is the next concept regarding the textbook? You are having about oxygen. What are you having about, children? Oxygen, dioxygen. So regarding the dioxygen, how is the dioxygen prepared? Are the questions there in the textbook? You can once have a glance over the preparation of the dioxygen. These are somewhat storytelling. Much concept is there I had recalled. So coming from this dioxygen onwards, you can see its preparation. What is the preparation? We just got the word right. Potassium chloride. What is the formula of potassium chloride? Presently we are working with the dioxide. 2 moles of the potassium chloride on heating, they are decomposing to give potassium chloride and the oxygen gas. It is not only the source of preparation, you can prepare from their electrochemical series now. In the least electron the least elements in the electrochemical series, means they are not reactive much. So the least order, once you take like silver oxide, once you heat, that is going to decompose to give silver and the oxygen gas. Or you can heat the mercury oxide, it is forming metallic mercury and oxygen gas. Or you can heat the Pb3O4, it is forming lead oxide and the oxygen gas. Or you can heat 2 moles of lead dioxide, that is also forming lead oxide and the oxygen gas. So different sources are there. What is the another important point here is the oxygen is having a solubility of 3 point some decimal will be there cubic centimeter in 100 cubic centimeter of water. In 100 cubic centimeter of water. So once you see here its solubility is around 3.0 cubic centimeter in 100 cubic centimeter of water. That is letting the aquatic organisms to survive. Not only these methods of preparations of oxygen we can get it by the electrolysis of water. So even from the decomposition of hydrogen peroxide also we can get the oxygen. Coming for this oxygen, we can see the O2 molecule. The bond length here is around 1.21 angstroms. See excellent, there is a comparative study with ozone and the oxygen. Generally this ozone occurs in 2 of the isomers. In these 2 isomers, its bond length is around 1.27 angstroms. One objective question will be there. They will compare the oxygen and ozone for you. What are the bond lengths? So in oxygen it is 1.21. Here double bond and single bond is also there. So it is around 1.27 angstroms. Once you see these points, see children, we are having still the concepts about this O2. What are the concepts we have regarding still O2? Our oxygen that we are studying, it is going to react with both metals and also with non-metals. What are the reactions of metals with this? We can see it is reacting with calcium. Oxygen is reacting with calcium to form calcium oxide, or it is reacting with aluminium, to form the aluminium oxide. With non-metals like phosphorus, these are the reactions with metals. Coming with non-metals, it is reacting with a non-metal like phosphorus to form phosphorus P4O10, or with carbon it is forming carbon dioxide. At times we can also see some of the other reactions like sulfur dioxide gas is reacted with oxygen gas in the presence of a catalyst called vanadium pentoxide to be oxidized into sulfur trioxide. Or 4 moles of hydrochloric acid is reacted with oxygen in the presence of CuCl2 to give chlorine gas and a molecule of water. So you can see these reactions of oxygen. See the next concept. What is the next concept we have? We have the next concept regarding the oxides, simple oxides. Right? Let us see what are the simple oxides here. Simple oxides. What are the simple oxides, children? What are the simple oxides? In the simple oxides, actually there are many subtopics. There are many subtopics. What are the many subtopics we have in simple oxides? Like MgO or Al2O3. These are just called as the simple oxides. But once you see the combination of Fe2O3 and FeO, it is forming a mixture of oxide Fe3O4. So this is called as a complex oxide. It is called as a complex oxide. The same you can find with lead. Lead trioxide is combined with lead oxide to form Pb3O4. Pb3O4. So sometimes these mixed oxides, complex oxides we can call, or we can call these mixed oxides. It is red in color, Pb3O4, and so it's called as red oxide also. Coming for the metallic oxides and non-metallic oxides nature. Non-metallic oxide nature. Once you see any of the non-metallic oxides like sulfur dioxide or carbon dioxide. Sulfur dioxide when combined with water, it is forming H2SO3. Means non-metallic oxides reacts with water to form their corresponding acid. In the case of some Mn2O7 or K2Cr2O7, in which metal is in the higher oxidation state, even those also acts as the acids. It's not only non-metal that must act as acid. Some metal oxides in which metal occurring in the higher oxidation state will also act as the acid. Coming for the metallic oxides. Everyone knows this one. Metallic oxides when dissolved in water, they will form the corresponding bases. But there are some few metal oxides like aluminum. You please see the reactions in textbook. It reacts both with acids and also with the bases. Hence, it is called as the amphoteric in nature. What is the name called, children? Amphoteric in nature. Now, at last we can go for our ozone. How about ozone, children? Ozone. Once you see the ozone, what is the formula of ozone? O3. How is it formed? It is formed by the decomposition of oxygen under the UV sunlight. So when the UV rays falls on the oxygen gas, that decomposes into atomic oxygen, which further reacts with the oxygen gas to form the O3. Very important bit, very simple thing, but we'll be asking the question. How is the ozone formed? It is formed by the decomposition of oxygen gas under the presence of UV light. So this ozone can be prepared in the lab. How this ozone can be prepared in the lab means by a silent electric discharge. A silent electric discharge when carried with the oxygen gas, it is converted into ozone, which is of only 10%. If you want more ozonized battery, you must pass this one through the ozonized battery. Then you can get the pure ozone. The problem with this ozone is it readily decomposes to give oxygen, O2, and the nascent oxygen. So this nascent oxygen makes another substances to readily undergo oxidation. If you take lead sulfide, the ozone oxidizes the lead sulfide to lead sulfate. It oxidizes iodide in presence of water to give iodine. Here, whenever ozone is treated with potassium iodide, in the presence of a borate buffer, it forms iodine. This iodine is further reacted with sodium thiosulfate, and this process is used for the quantitative analysis of ozone. Very important JMA's question, quantitative analysis of the ozone. So these are some of the reactions of the ozone. We had already seen the structure of the ozone also. How is the structure of the ozone? It occurs in the two forms. two forms. This bond length you must find out 1.27 angstroms or 128 picometers they mentioned. So these are the points something related to the ozone. And now we can go with the allotropes of sulfur. Allotropes of sulfur. See here children, I had completely given a glance regarding the allotropes of sulfur. So your work can be easy instead of studying and forgetting those passages. See, the sulfur occurs in many allotropes, but we are dealing with only 3 allotropes here. That is called alpha. Only 2 we will discuss: alpha and the beta form. Alpha form we call as the rhombic sulfur. Beta form we call as the monoclinic sulfur. Right. This monoclinic sulfur is prepared from the alpha sulfur. Let us see first of all how this alpha sulfur is prepared. Alpha sulfur is prepared by heating rolled sulfur in a carbon disulfide solution. Then it converts into alpha sulfur. So rolled sulfur on heating in the presence of carbon disulfide, it forms our alpha sulfur or the rhombic sulfur. So from this rhombic sulfur, if you heat or melt it, it will form some crust. When we make some 2 holes in the crust and pour on the liquid, then we can get the colorless crystals of the beta monoclinic sulfur. So very shortcuts we had given here. Beta clinic is obtained from the rhombic sulfur only. So coming to their color, it's yellow in color. We know it does not have any color, so I left it colorless. Coming for the melting point, 385.8 Kelvin, whereas this 393 Kelvin around. Coming to specific gravity, 2.06 and 1.9, it will be the specific gravity of the beta sulfur. It is insoluble in carbon disulfide, but it is soluble. It is soluble. It is insoluble in water. First of all, it is soluble in many compounds like benzene. It is soluble, or ethanol. It is soluble. You can say either it is soluble in carbon disulfide. It is soluble, but this is soluble only in carbon disulfide. Soluble only in the carbon disulfide. So out of these solvents, any of the solvent can be questioned. Like they'll ask, which of the allotrope of sulfur is soluble in the following? Means then you must remember about rhombic sulfur, because monoclinic is soluble only in the carbon disulfide. Now coming for the temperature at which these are stable. If you heat this alpha sulfur above 369 Kelvin, that changes into beta sulfur. Alpha sulfur, if you heat above 369, that changes into beta sulfur. But below the 369, the beta sulfur will convert into alpha sulfur. So these both forms can be interchanged from one form to another. But at 369 Kelvin, the both will occur. It is called as the transition temperature. Very important point. At what time? At a temperature, both forms of sulfur will coexist. What is the temperature named? It is called as the transition temperature. How much is the value? 369 Kelvin. So if you heat these acid forms, means alpha sulfur or the beta sulfur, both will occur in the acid molecule. Above 1000 Kelvin, there is one of the form of sulfur that's called S2. In that case of S2, it behaves like O2 molecule. In O2 molecule, we know there are 2 unpaired electrons. That is in the pi star, 2px1 and 2py1, there will be 2 unpaired electrons and it will be paramagnetic in nature. So these are the key concepts regarding the allotropes of the sulfur. Now let us see about the sulfur dioxide. See children, the sulfur dioxide, you please read through the textbook. We had lot of preparations from the textbook, so please read the sulfur dioxide preparations from the textbook. Let us highlight only the important points regarding the sulfur dioxide. Then we will go with the oxoacids of sulfur. So coming with this sulfur dioxide, important reactions I am giving. It reacts with chlorine. In presence of the charcoal. To give sulfuryl chloride. As well as Uh, this sulfur dioxide is acting as a very strong reducing agent. Many times we highlighted the point. It is acting as a very strong reducing agent. So if you see Fe plus 2, whenever a substance is acting as a reducing agent, it is making another substance to undergo oxidation. It makes another species to undergo oxidation. So this takes place in the presence of water. Like ferrous is oxidized to ferric. Sulfur dioxide is converted into sulfate, and the remaining will be in the acidic form. Not only this, it oxidizes ferrous to ferric. In another MCQs also they will give which metal will be oxidized by the sulfur dioxide. We had seen in this case of ferrous is converted to ferric. We know potassium permanganate ion. Manganate ion. So that potassium permanganate ion from the +7 oxidation state, that is oxidized to +2 oxidation state. Once you see the reactions in the textbook. So coming for the oxides of sulfur. What are the various oxides of sulfur? We know, children. You please read the textbook. Manufacturing of sulfuric acid also you please don't omit. In the manufacturing of sulfuric acid, the important points to be remembered is H2S2O7 is called as the oleum. Once you see the oxides of sulfur, what are the various oxides of sulfur? Let us start with H2SO3. In this case, double bonded oxygen will be there. Here one OH and here one OH will be there. H2SO3. Coming for H2SO4. Here also double bond is there. Here also double bond is there. Here OH is there, and here another OH is there. Now, if you go in detail, two of the H2SO4 molecules, when you bring side by side, they will form the oleum. Means H2S2O7. H2S2O7 means what? Two of them are brought side by side. So they will have a oxygen linkage. Which will have the oxygen linkage? The two molecules, when they are lost the water molecule, they will form a oxygen linkage. Or if you see H2S2O8, they will have a peroxy linkage. What linkage do they have, children? They will have a peroxy linkage. For example, if you see here H2S2O6, between the sulfur atoms it will not have any oxygen linkages. Both sulfurs will be bonded directly. Or if you see H2S2O5, how do the H2S2O5 will be present? Means you give up one of the oxygen here. Means one double bonded oxygen you can remove with the structure of the H2S2O5. Then you can go with H2S2O4. H2S2O4 means even that will have only one of the OH group. Here also sulfur will have one of the OH group. Coming with H2S2O3. There, please see, one sulfur will be bonded with another sulfur. In this case, H2S2O3. Very important structures. In textbook only these three are given. which are given H2SO3, H2SO4, H2S2O7, H2S2O8 are given. But these are very important for objective. Which are very important for objective? H2S2O6, H2S2O5, H2S2O4 and H2S2O3. Got it, children? So note down the structures of oxo acids of sulfur. Sorry children, lighting problem is there up to now. I didn't identify. Please write down or take a snapshot of these oxo acids of sulfur. See children, here we are having some questions like from this topic that I had taught now. In which pair of ions both the species contain sulfur single bond sulfur? Sulfur single bond sulfur. S4 O6 2 minus, S2 O3 2 minus. S2 O3 2 minus means, for example, if you see our H2S2O3, H2S2O3, after losing two of the hydrogens, what will be the charge remaining? S2O3 2 minus, S2O3 2 minus, is it not? So that's what we call as the S2O3. Next, S2O7 2 minus, S2O8 2 minus, option C. The pair are S4O6 2 minus, S2O7 2 minus, S2O7 2 minus and S2O3 2 minus. So from these pairs you must find which will have only sulfur single bond sulfur linkages. Next, you refer the structures that are given now. The acid in which oxygen-oxygen bonding is present, means peroxy bonding is present. H2S2O3, H2S2O6, H2S2O8, H2S4O6. So you find out which is having peroxy bond. The species having no sulfur single bond sulfurs. S2O4 2 minus, S2O3 2 minus, S2O7 2 minus, S2O5 2 minus. You must find out which is not having sulfur single bond sulfurs. S2O8 2 minus have, S2O8 2 minus have sulfur single bond sulfur, sulfur single bond oxygen bridging, oxygen bridging and none of the above. So write down. I will just pause to write these things for you. Some children had question, sir, here S4O6 2 minus is there, no sir. What is the structure of that S4O6 2 minus? S4O6 2 minus. So see here S4O6 2 minus, S4O6 2 minus. Generally, in the case of these sulfurs, what we know, the linkage is there, means 3 oxygens left side, 3 oxygens right side, and between the sulfur and sulfur still one more sulfur and sulfur single bond is present. That's called S4O6 2 minus, S4O6 2 minus. So at last we can see here about the preparation of sulfuric acid and the properties of sulfuric acid. We are having very strong properties there, like it reacts with like water and acts as a very good dehydrating agent, and also reacts with carbon. Which one? Sulfuric acid in the formation of the dehydrating agent. This sulfuric acid is having a diprotic acid. At a time both H plus will not be given. First one of H plus will be given, in the next step another H plus will be given. So that acid dissociation constant of this H plus ion, sulfuric acid is very high. So it is acting as a very strong acid. Now these all points are covered in the textbook once you see. Up to now what did we learn, children? We had learned up to now group 15 elements and the group 16 elements. Still two more groups are there, that's called group 17 and the group 18. This group 16 related and the group 15 related, bit by bit you can go on answering. It can be shared on the screen. I may give some numbers to you. So in the next class we can see about group 17 elements synopsis. Then after we will go for the group 18. Thank you.